Hey kiddos, welcome to gas stoics. So up until now, you've just been looking at gravimetric stoichiometry, which is going from moles to moles, mass to moles, moles to mass, mass to mass. So gas stoic isn't that much different, except for the fact that you are looking at number of moles arrived by gas laws. And the only gases we're looking at are the only gas math that we're looking at are two. We have molar volume, which is your amount at STP and SATP, and your ideal gas law. So let's first take a look at what the heck gas stoich is. So gas stoichiometry is a procedure for calculating the volume of gases as products or reactants. Okay, and we're looking at two ways: molar volume and the ideal gas law. Gases also have a molar volume. Remember, it's liters per mole rather than concentration. And this is the conversion factor used to convert liters of gas to moles of gas or vice versa. And we also have the ideal gas law. Recall PV equals nRT. May also be required to find the number of moles of the reactant. So we can use the ideal gas law to find the number of moles of the reactant, or to find the volume, pressure, temperature of the product, or reactant for that case. So I'm going to give you examples of each. Okay, so here's an example. First example is if 300 grams of propane burns in a gas barbecue, what volume of oxygen? So we're looking for volume of oxygen, right, kiddos? And we have the mass of propane. And we also know that the conditions are SATP. So that's a lot of information. So don't worry about it. All you have to do, the most important thing, is to go ahead and populate your equation. Also, this is in your data booklet. There are 24.8 liters per mole of any gas at SATP conditions. So I'm going to add my mass over my propane. Now this is a hydrocarbon combustion reaction. Remember, it's your hydrocarbon plus oxygen yields carbon dioxide and water. That you have to know. That is something from grade 10. So make sure you know how to do a hydrocarbon combustion reaction. Anytime you are given mass, kiddos, remember you always have to have your molar mass, because you're going to be converting your grams to moles, then using your conversion factor, right, to go from moles of what you have to moles of what you need. I've identified the fact that I'm looking for volume of oxygen, and I've also written down the information for that. 24.8 liters per mole, because we were told that it's at SATP conditions. So first step, I always start with what's given. I have 300 grams of propane. This is my molar mass of propane. Now, oops, I'm going from moles of propane to moles of oxygen. This one here comes from the balanced equation, because there's no number, we assume it's 1. And these are the moles of what we're looking for. So this is what you have, and this is what you need. Now we're looking for moles, not grams. So in order to go from moles to liters, all we have to do is use this, the 24.8 liters per mole, as your conversion factor. You can have both ways, but what I want to do is I want to cancel out moles, oops, and get liters. So I have to go ahead and use this one so that my moles cancel out and I get my answer in liters. Now this, remember, is in your data booklet, so it's not anything you have to memorize. Let's go on to the next example. So now we have conditions at STP. Okay, so not SATP, STP, and that is also in your data booklet. And there are 22.4 liters per mole of any gas at standard temperature and pressure conditions. So what does that mean? It means you have 24 liters per 1 mole, or you know that the conversion factor can also mean 1 mole of any gas occupies 22.4 liters at STP. Okay, so hydrogen gas is produced when sodium metal is added to water. So we have sodium metal plus water. Remember, this is a single replacement reaction. For water, I would go ahead and write it as HOH, so then it's easier to do the single replacement. I'm looking for the mass of sodium is necessary to produce 20 liters of hydrogen gas at STP. Okay, so let's go ahead and balance our equation and populate it. Now, I feel that it's a lot easier to do HOH instead of H2O. This is a positively charged ion, and here's your positively charged ion, so these guys switch. And that's why you have sodium hydroxide plus H2 gas. Remember, it's a diatomic element, so you have to always go as H2 gas. I have 20 liters of it, and at STP, my conditions are 22.4 liters per mole. I've identified that I'm looking for the mass, so anytime you see mass, you go ahead and write the molar mass. Okay, kiddos? So what's going on now is we always start with what you're given, 20 liters. I'm using a conversion so that my liters cancel out, so I have to go ahead and use this conversion because I want to cancel out my liters to get to my moles. So now I have moles of hydrogen, and now I'm going to, oops, I'm going to figure out what the heck I'm looking for here, okay? So I have, this is for hydrogen. I have 1 mole of hydrogen here. That's where this 1 mole came from. And I'm looking for mass of sodium. That's where the 2 came from. This is sodium, and this one is for H2 gas. Now this conversion is going to get me to moles of sodium, right? I don't want moles of sodium. I want grams of sodium. So there you go. I introduced my molar mass, 22.99 grams per mole. My moles cancel out, and then I just use my calculator to find the answer. So that's example number 2, using STP conditions. Our last example has to do with the fact that you don't have STP, you don't have SATP anywhere, so it's going to be your ideal gas law. When you see a question that has volume, pressure, that kind of information, it's an ideal gas law. So we're looking for the volume of ammonia. So here we go. We have our pressure is equal to 450 kilopascals. We have our temperature, which is equal to 80 degrees Celsius, can be obtained from the complete reaction of 7.5 kilograms. So we have our mass of hydrogen with nitrogen. Okay, so don't worry about it. All we have to do is go ahead and write our equation, balance it out. Then we populate it. It becomes very, very important. Remember, we always have to change Celsius to Kelvin, always, because we're using the ideal gas law. And we're looking for volume. We've identified that. We have the mass of hydrogen and the molar mass of hydrogen gas. I changed it to grams just to make sure that it's easier for me to cancel out my grams. All right, so I'm going to start with what I have, which is 7,500 grams. I am going to use my molar mass to cancel out my grams. Now this is where my molar ratio comes in. This is what I'm looking for. I'm looking for my ammonia, and I have my moles of hydrogen gas. Okay, this is going to get me moles of ammonia. Now I use my formula, PV equals nRT. I have my moles of ammonia. I'm looking for my volume, kiddos. It's because it's asking for volume. So I'm going to rearrange my formula. V is equal to nRT over P. And I just fill in my info using my moles of ammonia. Now don't round until the very end, okay? So here we go. I have my moles of ammonia. I have my constant that's in the data booklet. And I have my temp in Celsius. And I also have my pressure that's given to you. So then all I have to do is use my calculator to find the answer. And my answer is 16,150.10 liters. and you're going to get your answer in scientific notation. Now, this will not be an answer in one of your tests. I won't make it like that. That would be rude. Okay, so let's just go ahead and summarize. You write a balanced chemical equation where you list the measurements, the unknown quantity symbol, we're identifying what we're looking for, the conversion factors for the measured and required substances. We're going to convert the measured quantity to a chemical amount using the appropriate conversion factor. You're going to calculate the chemical amount. Another word for chemical amount, kiddos, is number of moles. That's what chemical amount means. Of the required substance using the mole ratio from the balanced chemical equation, you're going to convert the calculated chemical amount, number of moles, to the final quantity, unless, of course, they're asking for moles. And we're going to use the appropriate conversion factor for that. So now we've gone from mass to moles to different moles to mass. Now, because of gas laws, we can start with any of these, use either the ideal gas law or molar volume to get to moles, to go to moles of another substance, and we can get to any of these. Obviously, for temperature and pressure, we use ideal gas law, right? And for volume, we can use either ideal gas law or molar volume. Okay, just to recap, molar volume is the same for all gases at the same temperature and pressure. Remember, all gases have the same physical properties. At STP, kiddos, this is in your data book, it is 22.4 liters per mole. At SATP, the molar volume is 24.8, okay? This can be used as a conversion factor, so I can go from liters to mole or moles to liters. And lastly, we compare Kelvin and Celsius. Remember, we have to convert always Celsius to Kelvin in order to use your ideal gas law. And we're just either subtracting or adding 27.3, oh, pardon me, 273.15 to either go from Celsius to Kelvin or Kelvin to Celsius. All right, I'm going to post some questions or complete the questions at the end of the note package, and I will also include the notes, the key. I'll do that today. Have a great day, kiddos. Bye.